This is my lab report video for Lab 6. So, as an introduction, the purpose of this lab was to investigate magnetic induction and eddy currents by analyzing how a falling bar magnet interacts with an aluminum tube and comparing observations to computational models. So, when we did the experiment in person, our time that we experimentally measured was 1.25 seconds falling, and our computational time was 0.973 seconds. The main principles that were used in this lab were the Biot-Savart law, the Faraday's law, and Newton's second and third law. So for our observed model, the initial conditions involved the bar magnet and the stopwatch. You can see some pictures of our lab experiment here. The system was the bar magnet and the aluminum foil tube, and the surroundings were everything else outside of it. So for our data, you can see the data table on the right. Our mass of the magnet was 0.026 kilograms. Our magnetic dipole moment was 0.477. And our tube dimensions are all recorded there. For the computational model, these are the initial conditions. So we set the values of the constants, we set the plot, and established the dimensions of the tube as well. For the actual coding, you can see here we made a function that represented the magnetic field of the moving point charge, set the function to calculate the change in magnetic flux over time, and then set another function to calculate the magnitude of the force on the ring for like a partial ring. For the computational results, you can see the graph here. It dips and then increases again and then stays constant and then goes back down at the very end. And the visual depiction is shown on the right. For some similarities and differences between the models, as I stated earlier, the experiment time took 1.25 seconds, while the computational time was 0.973 seconds. This isn't too big of a difference, but obviously external factors could have influenced this change. Like, we assumed that the bar magnet acts as a perfect magnetic dipole, but there were like surface imperfections and other things that would have resulted in some error. Also, our computational model assumed negligible air resistance, which wasn't reflective of the experiment, and the only forces involved were magnetic and gravitational when there were other forces introduced during our lab experiment. Some possible sources of error included electronic and magnetic devices in the surroundings, and creating other induced fields that affected the recorded data, friction against the sides of the tubes if we had misaligned drops, and the inconsistencies with starting and stopping the stopwatch when we're recording the times. For the what if questions, if the resistivity of the conductor was reduced close to zero by Ohm's law, that would mean that the induced current in the tube is much greater. Because the induced current would be greater current makes a greater magnetic force, so there would be a greater counteractive force as you drop the magnet through the tube, so it would slow it from falling and potentially even prevent it from falling entirely. If holes or slots were cut into the tube, it would disrupt the induced current in the aluminum. So this would just reduce the opposing magnetic force because there's just less material for the current to flow through.